So this is the lecture on convergent, different type of convergent. We already discussed the convergent in probability and convergent law for different random variable, sequence of random variable. So this is the important theorem, the third lecture on convergence of probability. So the different modes of convergence, Sorry. So we already discussed that if xn converges to x, then xn square converges to xn square x square, and if y is another random variable, then x and y converges to xn xy in probability if xn tends to x in probability. So there is important theorem, very important theorem is this. So let xn goes to x in probability. So in probability, and gb, and g is a function, be a continuous function, defined on in real number. So it is continuous function on real number. Then the important thing, that for any continuous function, g xn converges to gx. So it is not only just x squared. It is any xn, any function of xn. So xn cube converges to xn in probability. And in sin xn converges to sin x, everything, every continuous function as n tends to infinity. This is a very important theorem. So the outline of the proof is this. So since xn is a random variable, so we have this for given epsilon positive. So for any given epsilon positive, there is a real number. So there is a real number constant k, which is a function of epsilon, such that this probability of xn greater than k, that is some mod of x greater than k, the probability is less than epsilon by 2. So since for any random variable, this is some bounded, sort of bounded, not bounded, but is bounded by 1 minus the bounded with the probability 1 minus epsilon by 2. Also g is a continuous function. So since g is a continuous function, g is uniformly continuous. So g is continuous, and any continuous function is uniformly continuous. G is uniformly continuous on that minus k to k. So any continuous function is uniformly continuous on this closed interval. Actually, it's compact interval, closed and bounded interval. So it follows that. There exists a delta, which obviously is depends on epsilon and k both, such that g xn minus gx, this is less than epsilon. So this is uniformly continuous for every, and whenever this is true for actually all x, whenever that mod x is less than k, so it is less than equal to k, and that x minus xn, its mod value is less than delta. Now we consider three different sets. So A is such a set where that x mod x is less than equal to k. B is another set where this xn minus x is less than delta, and C is another set where this g of xn minus gx less than epsilon. We have three different sets. So you just look at the three different sets, A, B, and C, the three important sets, and we are going to use this set. So then what happens? Then if omega belongs to that A intersection B, then that must implies that omega n belongs to C. That is important. So that A intersection B is subset of C. Now, what is the probability of C complement? This is less than or equal to probability of A complement plus probability of B complement. Since A intersection B is a subset of C. So that is what happened? Then probability of that mod value of gxn minus gx greater than equal to epsilon is less than equal to probability of that mod of xn minus x less greater than equal to delta, and this probability of mod xn strictly greater than k plus is less than epsilon, which is both are epsilon by 2, so this is less than epsilon. Now, for if you take any n which is greater than equal to some n which is depends on epsilon, delta, k, all three, where this epsilon, delta are chosen in this as above, where this n, epsilon, delta, k is chosen, so that the probability of xn less than x, so this is strictly less than epsilon by 2 for all the epsilon greater than that n depends on epsilon, delta. So we have done this to prove that so we have this. So this is less than by k and epsilon by 2 and another epsilon by 2, sum is, so the probability of this is greater than epsilon is less than epsilon. So that means this converts in probability tends to 0. That g and xn tends to gx in probability. So the corollary is this. The corollary of this theorem is this. So xn goes to some constant p, where c is a constant, c is any constant, say is real number. Then if this, then that gxn for any continuous function gxn goes to gc, because c is just a constant random variable. You can just take a constant as a constant random variable as a degenerate at c, the constant random variable degenerate at c. So g being a continuous random variable, continuous function. This is a continuous function. So now this is very important theorem. Is this? So if any xn tends to x in probability, then this implies xn tends to in law. So probability is convergence some sort of stronger than in distribution. So if it is if the random variable converges to x, the sequence of random variable converges to x in probability, then it must converge in distribution also. So we are omitting this proof. You can just look at the Rodgi book. So next theorem is this. Let k is a constant. So k is constant. Then xn tends to x in law implies that xn tends to x in p. So is a sort of converse. If xn tends to p, where xn tends to x in p, then it implies that xn tends to x in law. And converse is also true if it is if k, sorry, it is k, not x. Sorry, it's not x, it is k. So if it is just a constant thing, then it is the converse also true. So this also proof left as exercise. And what is the corollary of this? The corollary is this. So if we'll, let k be a constant, then xn goes to k tends to k is if and only if this is an equivalent in law. So in probability convergence and this law in distribution convergence, they are actually equivalent. But the converse of for any other random variable is not true. So if xn tends to x in law, then may not be is converse to in probability. So now there's a example where we will show that that if some sequence converts to some random variable x in distributive law, they may not be in probability, converts to in probability. So what is this? This is like that. So let these are identically distributed x, x1, x2. These are all identical distributed or identical random variable. Identical distributed. It's not IID. It is just identical distribution. Is not independent. And the joint distribution is this. So this is the x distribution of x, and this is the distribution of xn. 0, 1, x or can take 0 or it's just 0, half, half 0. So it is not independent. Obviously not independent. So this is total marginal is half. Half this is a marginal, half, half. So it is very easy, uniform sort of joint distribution, and this is a marginal uniform. Now this is not independent. This is just identical. Now what happened? Now this is obviously the same distribution. So therefore what happens? This is xn converts to x in law because it's just the same distribution. It's like constant sequence. Same distribution. Xn all are same. x1, x2, xn all not independent, same. X also the same. But what about the probability convergence? So what is the probability of xn, the mod of xn minus x greater than say half, or any epsilon say epsilon equal to half? And this is just greater than equal to probability of xn minus x is equal to 1. Just 1. And what is 1? This is 1 is 0, another is 1. Xn is 0, x1, and x0, xn1. And what is this? This is just 1. This probability is 1. So it's not equal to 0. It cannot goes to 0. So it is therefore xn not goes to x in probability. So this is very important. And eventually the one more important thing is this. One more remark is this. If this is a probability convergent, may not be in moment convergent. So actually the moment convergent is stronger in some sense. So another remark is this. Xn may converge in probability, but xn whole to the power k, that expectation of this kth moment, that is a kth moment, may not converge to. So actually does not imply. We should write that does not imply. It does not imply that. Doesn't imply that is converged to in kth moment. There is no moment convergence for any k and k integer. And definition is this: let xn be a sequence random variables such that expectation of that mod xn, the rth moment actually is say finite for some r positive, and we say xn converge in the rth moment. So if this is true, then it's called in the rth moment, rth mean, sorry, or rth mean. It's a raw moment to an random variable x if that expectation of xr that is finite, and this expectation of their difference mod of xn minus x, the rth moment of this rth order moment, this converges to 0 as n tends to. So if this difference of this that rth power expectation of that is converged to 0, then it's called it is converged in rth mean or rth moment. And what we write in this case that the sequence of random variable, the sequence of random variable, and we write that xn converts to x in rth moment, so it is just r, small r. Now theorem is this important theorem is this, let xn converts to x in r for some r positive, then xn converts to x in probability. So that rth moment is sort of stronger than the in probability. So probability convergence is stronger than that in law, and that probability convergence is stronger than law, and this rth moment convergence is some sort of stronger than in probability convergence. And we there is a question whether the converse is true or not. Now the next theorem is this. It's also just left as an exercise. This is easy to see. The next theorem is this. So if xn is a sequence of random variables such that xn goes to x, let is a second order. So it is 2 r equal to 2. So it is a second order mean convergent. Then the first order mean also converge. Expectation of x goes to expectation of x, xn goes to x, and this expectation of xn square converts to expectation of x square as n tends to infinity. So this is very important. The proof is using that Cauchy-Schwarz inequality. The proof is the outline of the proof is this. So expectation of xn mod of it is just xn is 2 just here xn sorry not n is true, the r is true. The expectation of sorry it's just mod is outside here. So mod of that expectation, we know this is less than or equal to expectation of the value of the mod. So expectation of mod xn is mod x is mod of expectation of x is less than expectation of mod x. So it is this, and this is just less than or equal to the expected value of xn minus x whole square, and then whole to the power minus whole to the half, so root of that, and that we by definition this converts to 0 as n tends to infinity. It is given. Now how do show that this expectation of xn square goes to exponent x square? So we just write expectation of we have to use the Cauchy-Schwarz inequality. So we just write expectation of xn square is just expectation of xn minus x whole square plus expectation of x square, and then plus twice expectation of that x into xn minus x. And we see that this part goes to 0, this part goes to 0. It is given to us. And what about this part? So now expectation of this part is actually by using Cauchy-Schwarz inequality. This part is less than or equal to root over that expectation of x square by it is a Cauchy-Schwarz inequality expectation of xn minus x whole square. So again, this goes to 0. It is given to R. So this also goes to 0. That means this expected xn square goes to expectation of x square. So using Cauchy-Schwarz inequality, this part is 0, and by given condition, that first part is 0. So in the second order movement converges, then second mean converge, and the second order movement also converges, and that is a variance also converges. So that means the corollary is this: if xn in x, that implies variance of xn goes to variance of x. We have this variance convergence. And if there is two, if it is a two sequence, xm and xyn, the two sequence of random variable, sequence is of random variables, such that xm goes to x in second mean, and yn goes to y in second mean. Then we have this, the product, the expectation of xn into y n or into xm, that converts to x expectation of x into y, the double limit, as n and m both converts to infinity, just to infinity. So this is very important, and that means that is the therefore together implies whatever. Therefore the corollary, there is another corollary is this, that if xm goes to x in 2 and yn goes to y in 2, then their covariance, also covariance of x m yn goes to the covariance of x and y. So this is the previous two thing. And it is not only true for the second, it is also true for the any rth mean moment. So next theorem is this: if xn goes to x in R, then expectation of mod xn rth moment converts to expectation of mod of x whole to the power r. So this rth moment is also converge, and if other theorem is this, the very important theorem. Let say r is greater than s, then xn goes to x in R implies that the higher order implies the lower order. Actually, xn goes to x in s. It's s mean. So if the third mean convergence, the second mean also true. So higher order mean convergence implies the lower order mean convergence. This is just an easy thing using the inequalities. So we have this thing for three type of convergence. There is the last type of convergence, the strongest type of convergence, actually, which implies all this convergence is the almost surely convergence. This almost surely convergence is the strongest type of convergence, and we will discuss in the next lecture the almost surely convergence. We already discussed the other three convergence. In the next class, we discuss the almost surely convergence.